Hey there, here we go into Euler's method, which is a method named after the mathematician Euler, who came up with this terrific way of approximating values of solutions to differential equations. And you might be like, wait, what? So let's go over the process first before we figure out what it is that this thing is doing and how it works. We're going to actually just do the process. So this says the differential equation dy dx equals 2x has the particular solution y equals f of x with initial condition f of 0 equals 1. So what that means is you have a differential equation. You have some solution in that differential equation is y equals f of x. And we've got the initial condition, or the point 0, 1, is on that function. We're going to use Euler's method starting at x equals 0 with 4 steps of equal size to approximate the value f of 2. By the end of this video, you're going to know how to do this process. So what this process essentially does is we're going to use a lot of tangent lines, basically, to this curve using the derivative and the fact that we have a starting point to approximate f of 2. Yet we're never going to actually know what the original curve was. Very cool. So a lot of tangent line approximations. So here's Euler's method. It literally says that the y value that you want to get out, right? So whatever the y value is approximately going to be the starting y value. We often call that y sub 0 or y naught plus the derivative, so dy dx, evaluated at some point, right, wherever we are. So I'm going to put a line there that says evaluated at some value x comma y at the point times delta x. And if you think about this, this is the same as saying the initial y value plus the slope times the change in x, or b plus m times x. Almost. It's more like point slope form. So let's dive into it and use it. So I'm going to do my first step here. And the question is, how wide are my steps? If I'm going to do 4 steps of equal size from 0 to 2, well, the overall width would be 2 minus 0 with 4 steps. This gives me delta x. So delta x is going to be 1/2. That's my width. So all we're going to use each time is 1/2. And to get my first y value, what we're basically approximating is f of 0.5. You're going from 0 to 0.5. We're going to approximate 1/2 later, right? 1/2 down we're going to go. That's approximately equal to our starting value, which is 1, plus the derivative, which is dy dx, at the point that we're currently. So where are we? We're currently at 0, 1. Times delta x. And I'm not going to write out this mess of notation each time. So that's going to be equal to 1 plus the derivative at 0, 1 is 2 times 0. Right? So the derivative at 0, 1, you just plug in x equals 0 into your derivative. That's 0 times delta x, which is 1/2, which equals 1. So what this means is the point 0.5 comma 1 is basically the tangent line approximation. So the tangent line to this curve at 0, 1 at 0.5. So we're basically saying if we go out to 0.5, the y value on that tangent line is 1. Now we take this number and we say, let's assume that that point, that number, is on the curve. It's not, but we're going to assume that it is. And we're going to use that to find the tangent line at 0.5 comma 1 using this slope. We're going to do it again, basically. So f of 1 is approximately our starting y value, still 1, plus dy dx. I'm not going to plug it in like this each time. It's dy dx at 0.5 comma 1. So you plug in 0.5 into the slope, 2 times 0.5. That's the derivative at the x value 0.5. And we multiply that by 1/2. Well, that's 1 plus 2 times 0.5 is 1 times 1/2 is 1/2. So you get 1.5 or 3/2. Okay, what does this mean? Well, we just went to a value of 1, and f of 1 is approximately 3/2 or 1.5. Approximately. Is that point on the curve? Oh no, definitely not. But it's an approximation. Let's do it again. So now we take f of 1.5. That's what we're going to approximate. How do we get there? Well, what we do is we start at the point that we're assuming is on the curve, even though it's not. We add on to that the slope at this point times the amount that we're going to travel, the 0.5 or the 1/2. So the derivative is 2 times the x value, and that's going to be 1 in this case, times 1/2. Okay, so what's that going to equal out to? Well, 3/2 plus 2 times 1/2 essentially is 1, and 3/2 is 5/2. So now this is the point 1.5 comma 5 halves. So I'll write that, I guess, as a decimal, 1.5 comma 2.5. Okay, so what do we do from here? Again, we're going to assume that this point is on the curve. We've done 3 steps so far. 1 step, 2 steps, 3 steps. We're going to approximate f of 2 now. This will be our answer when we're done. So we do the same thing. We start at 2.5, the y value that we're assuming is on the curve even though it's not, plus the derivative at 1.5. That's where we're currently at, 2 times 1.5. And then we're going to travel a distance of 1/2. Okay, well, 2.5 plus 2 times 1.5 is 3 times 1/2. Well, what's that going to be? That's going to be 1.5 plus 2.5 is equal to 4. So that means that when we plug in 2, we approximately get out a value of 4. Okay, so what just happened in all of this? What was that all about? We just figured out that f of 2 was approximately 4, and you're probably like, pictures please. So that's the process. And in a later video after this one, we're going to go over more examples. So the process is not so bad, but let's go over the concept a little bit more. So what just happened is dy dx is equal to 2x. And we know that the original point is 0, 1. We're told that. That's the initial condition. If you integrate this, you'll get y equals x squared plus c. So that's actually the solution of the differential equation. And when we plug in 0, we'll get out 1 for c. So we get x squared plus 1 is actually the equation of the solution curve. So we're approximating points on there, but I'm using a curve that we can find. This is actually great for differential equations that we cannot solve for or cannot solve for easily, so that we can still get approximations of values of the solution curve. So what did we just do? Well, what we just did is we said we have a point 0, 1. We went out 1/2 and found that the slope was 0. And we got there, and that was the point 0, 1. If you remember, that was our first approximation. So that was the first approximation at 0.5 comma 1. Then we pretend that this point is on the curve. So we use dy dx at that point to find the slope at that point, and then added it onto the y value when multiplied by delta x. It's basically like taking another tangent line, and that gave us yet another value to go up by. And I'll go over to that, and that value was 1 comma 3 halves. So that was over to here. So here's 1 comma 3 halves. Oh, so you went 1 comma 3 halves, and then the next value after that was 1.5 comma 2.5. And so that was up to here. Oh, there we go. So we get that next point. And then last but certainly not least, we ended up at 4, right? So we ended up at 2 comma 4. So it should not be curved. It ends up being basically like lines that trace out this curve. And so that approximates the true value. I mean, it's not the exact value, but it approximates it. So that's it. This is actually a huge connection piece, as I said down here, to a much more accurate approximation of curves called Taylor polynomials. We'll get to that towards the end of a BC calculus or a Calc 2 course. So if you're viewing this in your Calc 2 course, this will connect greatly with that. But that's it. That's Euler's method. I'll see you in the next video when we go over some other Euler's method problems. We just go over the process. And then there's one more video where I prove to you that this is just a lot of tangent line equations. I'll see you there. I'll see you then. Peace.